happy to be here and really happy to be meeting you all. I also have Vamsi with me. He will be assisting me with the demo. We actually are going to go through how do you build real-time data streams, why do you want to build it, and also look at a live demo on the Confluent Cloud. But before that, let me start with a brief introduction. I'm Pradeep Reddy, Director of Engineering at Confluent. And at Confluent, I lead the overall engineering team. Prior to this, I've been with startups, founded startups. Prior to that, I was with multi-billion-dollar companies like Salesforce, and been in Bay Area and India for the last 10 years. Vamsi, do you want to introduce yourself?
Sure. Hey, hi. I'm Vamsi Krishna from Solutions Internet from Confluent. So I speak to a lot of customers in India and APAC region, give them solutions on Confluent, make real-time data streaming a reality for them and for their businesses. We'll see more in action after the live streams.
Awesome. Thanks, Vamsi. All right, with that, why don't we jump right in? So before getting into how do we design data streaming or how do we design the architectures of data streaming, I really want to focus on why do we need real-time data? Why do we need the data to be real-time? And what is changing? What is causing this to happen? So I'm going to start with a brief slide over here. So the world has been changing. So the world has really changed over the last 10, 15 years. If we go back like 10 years, the expectations that we had from various systems was fundamentally different. And that is where, like, if you look at the kids over here, they don't know what this device is. They're just trying to figure out, versus like something like a mobile phone, they completely understand and their expectations are very different. So moving on with, as the world is changing, so is every aspect that we touch upon. So previously the banking was something more like brick and mortar where you would walk in and go there, versus now it is completely real time. Our expectations are changing. We are becoming fundamentally more impatient and expect things to be in real time. And that is where it is very important that the software also changes. If you look at the software that was built or designed like 15 years back, they were fundamentally very batch-oriented, slow, and the expectations were such. But now the expectation is that the data is in motion. It's more real time. And that is where all the expectations are changing. If you look at the taxi services, I mean, we were fine with waiting for a taxi, just calling them up, versus what we expect now is a precise location where they are and knowing what is happening at what point in time. Same with the groceries. If you order a grocery, you almost would accept like precise timing when it's going to get delivered. So fundamentally, our expectations are changing. We know, like, we almost becoming very impatient, and that is where I think it starts becoming very important for us to start looking at software where the data is more in real time. Moving on, if you look at the old software interfaces, and this was fine because our customer bases were completely comfortable with like the old way where it was slow, batch processing oriented, siloed, versus now with the new expectation from the customer base, it's much more, the expectation is that because the data is fast, you're getting notifications in pretty much near real time, if not real time. And that's where the real time data processing becomes super important. And that's where, and all the data are also becoming super connected. We want to essentially get all the data together, be able to analyze this and create real-time predictions for it. Very similarly, you always want to know instantaneously when a particular action has occurred. It's not fine for you to know about it 24 hours down the line. So similar, like you want to know that the order has been picked up, it will be delivered in the next 5 minutes, it's on the way. So it's completely real time that you really want to unlock your data and make it available in real time. So moving on, now, given this context, if you look at it, previous softwares or the softwares that we were designing like 15 years back were fundamentally designed with an expectation where it's okay for things to be delayed. And that is where we were, like most of the databases, most of the SaaS applications were islands of data that used to exist, sprinkled across the ecosystems, and the apps would fetch it or there would be batch processing that would happen. And all of this data was sprinkled across the ecosystems, and it was fine because most of the processing was batch oriented. It was fine for us to essentially get updates once in every 24 hours. But moving on, I think if you look at like most of these previous architectures were fundamentally based on databases which operate on data at rest. And slow daily batch processing was the expectation over there versus something that is more real time. So fast forwarding is we have to cater to the expectation our customers are looking for, which is essentially they want to know all the updates in real time. They want to know what happened like a couple of minutes back, how precise expectation of what is changing. This is the architecture that we need to start going towards. And that is what we will start clicking into and going into. What does it take for us to get into this kind of paradigm and get into this. So instead of databases being the heart of the nervous system or the central nervous system, it's very important to have something which can cater to the real-time stream processing, which is consuming data from all the sources, collating data from all the sources and making it available for rich front-end customer experiences, enabling real-time back-end operations, enabling real-time fraud detection use cases and like this. Moving forward, so how do we make this happen? So, as we talked about, I think it's extremely important for us to unlock the data, make it completely available, and what we call this as like a data emotion is the central nervous system for any company. So how do we make this data fluid and available in real time? How many of you have used Apache Kafka or have heard of it? That's all. So that's, it's an open source system that has came into existence almost like 10 years, 10 plus years. And let me jump right in. So Apache Kafka started in 2010 and it quickly became like a de facto pattern of like enabling real-time communication and real-time streaming. And we at Confluent, like Apache Kafka was authored by the founders of Confluent, and Confluent is one of the biggest contributors, open source contributors for Apache Kafka, and we essentially are on top of it to make sure that Apache Kafka is progressing and scaling to the needs that are expected and needed for the today's world. Almost 80% of the companies, Fortune 100 companies, essentially use Apache Kafka today, and it's pretty much become the de facto of how companies have started moving towards a more real-time oriented architectures. Again, 70% of the Fortune 500 across various use cases, whether it's travel, whether it's finance and banking, insurance, telecom, have been using Apache Kafka. Now, with Apache Kafka, I want to dig deeper into like what does Confluent do and start getting into the architectures of the Confluent, what Confluent enables. So if you really look at like what we were looking at, instead of highlights of the data, if you wanted to make our data fluid, how does Confluent help? And what is the Confluent architecture that enables this with a single click in a fully managed Confluent Cloud environment? So Confluent Cloud essentially enables, we have a huge number of connectors, which is what you're seeing on the left. So you could essentially connect to any of your databases, any of your point of sale systems, you could connect to any of your ERP systems. And Confluent Cloud, on a click of a button, will essentially enable ingesting this data into a fully managed Kafka which we run on the Confluent Cloud. So once you connect to it, all of this data that is sprinkled across or isolated would start becoming completely available in real time. And you could enable things like change data captures, which is like as and when you update any of the source systems which support CDCs, you could essentially start listening to these change events within the Confluent Cloud from the Kafka. And we also provide what we essentially is like ACD stream processing, where you could essentially take this data, enrich the data, transform the data, analyze the data in the real world. And finally, you might want to use this to essentially send out email notifications or updates, or use it for real-time monitoring and dashboards. But at a very high level, this is how Confluent works and what it enables. So we'll dig deeper into what is needed for each of these systems and how would you be able to unlock your data to be available in real time. So the first thing is, for you to be able to unlock, and if you go back, the first thing is, if you look at the things on the left, all of these systems, you want to be able to connect to these systems. It's not easy for you to just rip and replace each of these systems. So you essentially need a way for you to be able to connect to these systems, capture the data in real time or in near real time, and pull this data into the cloud, into the Confluent Cloud, into the Kafka. So using our what we call as Kafka Connect, which is again an open source framework which is available in the open source community in Apache open source. We have built hundreds of connectors which essentially work on the common framework, common platform, which can consume data in near real time from various source systems, make it available for downstream processing. And Connect is fundamentally the primary one that essentially takes care of loading the data from various sources. And then also, eventually, once you have any models that you have built up, you could always dump it into one of the downstream systems. It could be MongoDB from the world, it could be any other application that you want to consume from it. And we have more than 200 plus pre-built connectors. So depending upon your use case and the list of sources and things that you use, you could go to the cloud, select the connector that is needed, connect it back to your system, start unlocking the data for sources or for things. Now the second part of it is, we also want to make sure that you have enough decoupling between the systems, that you don't want information about what is the source producing and what is the consumer essentially consuming this data. And that is where this abstraction becomes very important when you're thinking about building decoupled microservices. Schema registry is basically, think of this as a data schema registry, which would essentially let you define the schema, the shape of your data that's being produced into a particular topic. And there is again something that's available out of the box and something that you can just configure saying that these are the different topics and these are the schemas for each of the topic. And schema registry would essentially make sure you can enable forward progressions or backward schema migrations as such. And we support various ones like Avro, JSON protocols, and the serialization, deserialization formats and all this. And schema registry is super important to be able to build decoupled systems so that your source and the sink doesn't have to know about who is producing and what they are producing, and leads to helping you with like schema evaluations over time. Moving on now, we talked about various databases, we talked about the connectors, which can let you ingest the data into Kafka. There could be different applications that you are building, which would again be loading the data and publishing it into Kafka. But there is more to the stream processing. I mean, at this point, you want to essentially not just unlock the data into Kafka or into the system, into the Confluent Cloud, you also want to do some stream processing. You might want to do rolling window lookups. You might want to do joins of the data across different sources. You might want to do basic stream processing. You might want to do aggregations and joins and summations and various analysis. And that is where there are a lot of virtual systems that exist in the market. Like Spark is one of those, Storm is one of those, and likewise I'm sure you guys have looked into various similar stream processing applications. But what you would quickly realize is each of these systems are extremely difficult for you to run and manage. Like I've personally been involved in building huge big data systems. I've personally been involved in the last 10 years building and deploying one of the biggest Spark systems and also been involved with Flink and likewise. But what you quickly realize is you're investing about 80% of your resources not to build the business use cases, but really to essentially operate these at scale. Is it running? Is it observability is in place? And likewise, and that's what makes it really difficult, because each of these systems are pretty complicated. And that is where what Confluent Cloud, which is a fully managed service out of the box, offers is, on the left you are able to ingest all the data, but we have something which is basically which can enable us to do various stream processing, what we call as KSQL-DB. KSQL-DB is the compute layer which can run, like it works on SQL as abstraction. It could essentially run various stream processing jobs that you essentially create materialized views for your applications to consume the data from, pull the data from in real time. And think of this as the modern database or the modern compute layer which can enable you to essentially build it. Over and above this, we are already also investing on Flink, fully managed Flink. We recently acquired a company which enables us to bring in a huge Flink community into our ecosystem, into Confluent. And we are also bringing in Flink for additional use cases that can help us further enhance the real-time processing capabilities for building more complex architectures. Now moving on, KSQL-DB, as I told, this is basically the compute layer on top of the Kafka, which could let you create various aggregations, various joins, filters, and there is also user-defined functions where you could essentially create a piece of code that could be called out for while you are doing the processing. There is also like very simple embedded connectors as a part of this. We'll see a quick demo in a while, which will go into the details of using all of this architecture, how do we enable real-time monitoring. So we will just dig deeper into each of these things in a bit in a live level. But putting all the dots together, like if you look at how the eventual architecture looks like for us to enable real-time streaming and real-time processing, it's really a bunch of connectors that exist on the left side. Using Confluent Cloud, you could directly click on it, configure, point it to your respective sources. It could be your Oracles, it could be your PostgreSQL, or it could be any of your SaaS vendors like Salesforce. And make this data available for downstream applications into various Kafka topics. Then use KSQL or Flink to be able to do this processing, enrich this data, and make it available again to your downstream systems in a more enriched manner. It could be like data learning models that you are trying to build, or any of the other systems. And these sync connectors, once you have enriched data, you could decide to store these materialized views in one of the downstream systems, or store this one, or push this to the end users to other systems. So this is at a very high level how the overall system looks. I mean, though overall it looks like the whole process that we went through sounded very complicated, like what we try to do as Confluent is just to make it extremely simple. Provide out-of-the-box observability, make sure that it's highly reliable. We take care of making sure that it is running on the right regions, and we take care of all the disaster recovery, zero data loss, and making it extremely simple for our customers so that the customers can really focus on building their business applications, building their business use cases, and which is needed. Moving on. So what problems can we solve with Confluent Cloud? I mean, there are various use cases that we have seen over the last 7-8 years at Confluent. Essentially, there are various data infrastructure use cases that can be solved. There are various business application use cases that we have seen cloud being applied. There could be data pipelines that you're building. There could be data warehouse modernization that you're doing. You might just be doing log aggregation or creating a scene kind of a system. Or you could be doing more business application use cases, which is more like how to create a 360-degree view of the customers. You might be getting feeds of data about the customers from various sources. It could be, let's say, sources of the world, your own Oracle databases, it could be your own systems. And that is where how you create a 360-degree view and create like a churn analysis, for instance. And that's where customer 360-degree views become important and very useful. IoT is another big space. We have seen a huge application. Cybersecurity is another one. Anomaly detection, real-time anomaly detection is another huge one. I mean, we'll take a quick look at the anomaly detection use case as a demo, as we walk into like how we build it. But anomaly detection is typically useful when it is in real time. If you get to know about anomalies after 48 hours, it's good information to have, but it is not action. And that's where trying to make it real time is one of the big action, one of the big things that Confluent unlocks. We have seen use cases across various industries, and none of these were built. I mean, Confluent is truly a platform where multiple of these use cases have become real over the past few years. We have seen use cases in retail, we have seen huge use cases in healthcare where they are connected health records. You're getting information from various sources. When you pick up your pharmacy from a pharmaceutical vendor, how do you essentially make sure all of this data is going in real time? How do you essentially do early on like fraud detection, capital management, transportation, again, like numerous use cases, and other industries that we have been seeing a lot of use cases. So this is one other one, like not just building real-time stream processing pipelines, like Confluent really also helps improving the developer speed and productivity and time to market. When you're thinking about like moving to more event-driven microservices architecture and modernizing this one, there's another space where we have really seen a huge application. You don't want two services to be talking to each other directly, knowing about like where to reach out to this one. So decoupling becomes extremely important as a design pattern. And that's where Confluent or Kafka as a source essentially makes it extremely simple. Instead of each of the application talking to each other, like trying to decouple it so that each application can roll out and basically move at its own pace. So this is another big space that we have seen where event-driven microservices has been a big application that we have seen. And before we move on, I think like this is another use case, and we will double click on one of these use cases, but why don't we essentially jump right into the demo. And the demo that we will be doing, and I have Ansi over here who would be driving the demo. The demo that we will be doing is more like a real-time fraud detection use case. And we'll walk through the actual code, how we build it, and how we essentially use all the tools that we talk about. Thank you.
Cool. So I think you have heard a lot from Pradeep on what Confluent is, how you can build real-time use cases there. Let me tell you what you can take away from this demo, right? What comes to your mind when you think of the term called DSP? Police, audio movies, music director. Today I'm going to give you a new definition for DSP, and we're going to see that in action. DSP for us stands for Data Streaming Platform. let's get right into the demo and see it in action. Cool. Now what you're seeing in front of you is a Confluent Cloud Console. It's running fully managed on AWS, Azure, and Google. Specifically, this is running on AWS, and I have built a stock trading platform, a live platform. What is happening in this platform is there are users who are signing up, and all the information of the users is going into a database. And there are live transactions that are happening, and that is going to another data system. And we are going to see how I have built an anomaly detection system using Confluent. Now, let us get to a pictorial view of what we have built. This is a very unique feature that we have built as Confluent called Stream Lineage. Now, whatever you build using all the components that Pradeep mentioned, connectors, Kafka, KSQL, queries, and all of it, everything gets automatically generated into this pictorial view. Now, what I have here, like I said, is all the users who are signing up, all their data is going into Postgres database, and all the data is being loaded into Kafka using Postgres source connector. Right? The connector will automatically pick the data. You don't need to write your own producer code. It comes and sits in user topic. The second thing is transactions. Live transactions are happening in the platform. People are buying stocks, people are selling stocks. All that live data is going and sitting in MongoDB. A sample of such a transaction is shown. Now, I am going to use another connector, in this case MongoDB, a class source connector, to take the data from MongoDB and load it into Kafka. Now we have both the data, what we want to work with in Kafka. If it is open source Kafka, your role actually ends here using the write consumer, take the data out, and further do the processing somewhere outside as a batch process properly. Now what I'm going to here show you is the magic of Confluent after the data comes into Kafka. Now let us see what we have built in our stream processing engine, which is KSQL. Now switching over to that view of what KSQL is, everything is already tightly integrated like Pradeep said, and all of them are part of the cloud. You don't need to do anything for that. Now, within a stream processing engine, you again have a pictorial view of stream processing capability alone, what is being built. Now, Kafka, like most of you have raised your hands when Pradeep asked when you use Kafka, so you might already be aware that Kafka is not data aware. It just sees everything as bytes, whatever you give. So first of all, we have to give awareness to the data, that is where schema registry also helps, and we have some automatic capabilities as well. Now when I load users data, I give the intelligence of users data, and I want a materialized view and the latest information of every user. So I load it into KSQL as a table. Second, I have all the streams, stock transactions happening. And I want all the transactions to be coming as an immutable set. None of the transactions should actually get lost. So I load stocks and all the transactions as a stream. Stream is an immutable, append-only kind of set, where again it is fault-tolerant, durable, and persistent. Now let us have a look at the sample data, how it is looking like. What you see on the right side is live transactions happening, a lot of data getting populated and changing very, very fast. That is an example of a stream. Now let us look at how the data is looking at in a table. Switching over to what is happening at a table level. So users, like I said, is a table and it only maintains the latest information of every user. So when I switch to table view, you only see all the users and what is the latest information, what is the latest email ID, phone number, and other attributes of that particular user. Now we have the data in place. We have loaded the data, we have given the intelligence of how to read the data for the stream processing engine. Now we are going to look at what kind of transformations you can go and achieve the use case itself. Now, first thing I'm going to talk about is a simple stateless transformation, which is a merge. I'm taking all the data from stocks transaction. The information is insufficient. I actually have to do a lookup. Instead of actually making a REST API call to a database and doing all of it, I have the data here and I'm simply writing a SQL style query to do the lookup, enrich this information, additionally add some filters. I may not need all the information. I'm just picking up what are the fields of interest for me. I'm doing specifically a left outer join here, joining on a primary key, and then loading the data out. All of this is happening in real time. Now let us have a look at a real example of the output of the same data now it is enriched with additional information which came as part of the lookup. This is a simple example of a stateless operation that I have performed. Moving on now, let's look at what other kind of transformations, what other kind of processing you can do on this particular platform. The next thing what I'm going to show you is a stateful operation that I'm going to do. If you look at the query here, there is something called count written there, so it is actually counting. One simple use case is I want to actually know for every particular stock symbol how many times a particular stock is being bought. So I write a simple query, and as a result of that query, what happens is I get to know what are all the stock symbols and how many times that particular stock has ever been bought. So this is good to know which stocks are performing well, which are performing low, and all of that. Such information can be got from here. But now let us focus on how to get more towards the anomaly detection, which is the primary use case for this demo. Now, adding on top of this particular stateful operation, I am introducing windowing now. I don't want global counters from the beginning of time. I want to actually count things at a particular window. Here I am using a 5-minute tumbling window for that operation. So when I do that and I do the counts, it is going to create a table, and the table will have stock symbols, and then it will have windows created for every 5 minutes, and it does that particular stateful operation to be counts or sum or any other aggregation of that type. So let's look at a sample of what the outcome of this particular query is. Again, stopping, pausing, and looking at it. So you see the same symbol on the left, but windows are different. There are different windows of 5-minute duration created, and when I go to the right, you see quantity updated for every 5 minutes. Hold on, but the problem is, here that time is not friendly to read. Anybody cannot simply infer from whatever is there because it is an epoch time frame. Now let us look at how we can leverage some more functionality of stream processing engine. KSQLDB has a lot of built-in functions, and to show you an example, I have just picked one of this to see how we can make that into human readable format. Additionally, progressing on our anomaly detection use case, what I'm doing is I'm first using a function to convert that epoch into human readable timestamp. Apart from that, now instead of looking at it in the stock symbol perspective, I'm going to look at all the stocks with respect to accounts. For every account, user account, how many transactions are happening in the same again stateful, aggregated, window fashion, counted. And additionally, apart from just counting it, I am going to put some logic in place to detect some anomalies. Assuming that more than 10 transactions are kind of an anomaly, I've put a count there saying it should all filter out all the counts which are greater than 10. Now looking at the output, what is going to happen is, now it is all not sorted by symbol, instead it is sorted by accounts, and then you have your normal epoch timestamps on the left, and additionally, what you are going to see is, you will have new timestamps created, which is human readable, and you have quantities on the right side, which are greater than 10. So this is one simple example of a logic which can detect an anomaly. Of course, you can define your own logic based on your business needs. You define your own logic and bring out the data what you want. Now, I have this in place, and I have found that what are those accounts which are problematic in nature. I want to further go and monitor only those problematic accounts so I can take further business actions to come off it. So this stream is going to monitor only such accounts which may be suspected as fraud. Such accounts are, for future transactions from such accounts are recorded in this new stream. So all the transactions from such problematic accounts are being recorded in this new stream called suspected fraud. Now, business can take multiple roads. You can take this information, plug it into the pre-trade flow, so actually you can stop further transactions happening from this account. Or you can maybe pause transactions for next half an hour or 1 hour or 1 day and put some monitoring in place. All of that could become complex, and in the interest of time, I didn't want to extend the pipeline itself. So what I'm going to show you next is, once you have the data of interest, whatever you want to make out of your business, you have the data in place. I'm going to simply use a connector, a sync connector, to dump the data out. You can take the data out in whatever fashion, using a consumer or using a connector, and give it to the point of interest. Now, switching back to the stream lineage view, the centerpiece is what we have seen, what was achieved using the stream processing platform. And last, what you see is whatever is a suspected fraud, all of that data I'm taking out using a MongoDB connector and dumping it into another MongoDB instance. Now, let us look at how it is looking like on the other side, which is MongoDB. So I have another database created, another collection created, where all of these suspected fraud transactions are loaded. Now, business, like I gave examples, they can take multiple actions on top of this particular data. Right? So this is an end-to-end view of how to load data, how to do some kind of processing, stateful, stateless, aggregations, filters, and all of it. Of course, you can write your own code if you need to, and also leverage the inbuilt functions, and finally take the data out so that you have a complete data streaming pipeline, a stream processing pipeline in front of you. Now, like I said, this is an auto-generated view based on if you know all the components, you don't build it. But what if you want to start from scratch? You want a reverse of this. Now, we have an answer for that as well. So what I'm going to show you next is Stream Designer, which is simply reverse of this. It starts with a plain blank canvas. You drag and drop all the components, whatever you want from the left, put it in the blank canvas, design your pipeline itself, put your connectors, topics, all the queries, put the logic in place, whatever transformations you want to do, and finally put where the data has to actually go. All of this, while you build on the UI itself, it also automatically generates a code on the back. Or if you don't really want to do it in the UI, but if you are a code fanatic, you can actually code everything and you will actually see it in the UI as well. Both of it is available, and you can either hit activate pipeline directly or take this, put it into GitOps and run it over, and so all of this will get done. Last but not least, I'll just show you one example of anomaly detection. There are numerous such examples which we have built and publicly made it available. So if you simply go to any search engine, type KSQL recipes, you will get a lot of such real-time use cases with example codes and example data to load and test for yourself. Please visit our booth. We have free cloud trial that we are giving with $400 credits. You can leverage that. You can look at all of these cases. You can put your own logic, build your pipeline, and make sense. So I hope I gave you a new dimension or definition of DSP, this data streaming platform. Next time when you want to actually move data in real time, set data in motion, think DSP, think confidence. Thank you.
Awesome. Thank you, Bob. That was fascinating to see how we build the whole pipeline in 10 minutes. Thank you so much.